This is the 27th lecture of the course MTH 204A, first section B. Recall that in the last lecture we were talking about maximal ideals and prime ideals. So, let me just recall for you. Suppose R is a, let us assume to be a commutative ring, and I an ideal. So, I is prime if and only if R modulo I is an integral domain, I is maximal if and only if is a field. Okay. So, what are the examples? The most natural example is suppose if our R is Z, then we see that all its maximal ideals are precisely the ideals of this form when P is prime. And also it talked about a ring which is very, very similar to that of Z, namely Fx, where F is any field. So, there all the maximal ideals are generated by irreducible. These are nothing, these are principal ideals generated by irreducible polynomials. Okay. This is what we have discussed. Now, today we will, so for today let us observe the following, that suppose for Fx to some R prime, where R prime is an integral domain, So, what about so this R prime integral domain? So, if is a homomorphism, so then kernel phi. So, this is a important observation here. So, kernel phi is either trivial or it has to be a maximal ideal, right. Why? Because Fx modulo kernel phi will be being a subring of an integral domain, it will be again an integral domain. So, therefore, these are, so therefore, the kernel is going to be a prime ideal, and inside Fx we have already seen that prime ideals and maximal ideals, they are the same, namely they are the ideals generated by irreducible polynomials. So, thus we see that either, so whenever we are having an homomorphism from Fx to some integral domain, we can observe that its kernel is either going to be trivial or it is maximal. Okay. So, also one more thing, let us observe that here. So, if F is C, so let F be C, okay, let F be C, then the maximal ideals are precisely these the ideals generated by of this form for A lying in C. Okay. Because over C as an immediate application of fundamental theorem of algebra, because every non-constant polynomial admits a root. So, therefore, we see the only reducible polynomials over CA in Cx, these are the polynomials in Cx are this linear monic linear polynomials. Well, of course, up to some constant multiple, but at the level of ideal. So, these are all maximal ideals of Cx. So, observe that the maximal ideals of Cx, let me put it down here. Ideals of Cx are in a bijective correspondence with points in C. Okay. So, in this, so this is what we obtain in view of this. So, in this lecture we will generalize this to generalize this to any polynomial rings over any number of variables, and this is exactly known as Hilbert's Nullstellensatz. Hilbert's Nullstellensatz. Okay. I write down the statement soon. So, in order to get into the Nullstellensatz, I should first talk about field of fractions of integral domains. So, as I said that let us postpone this discussion for a while. I will now first do here the field of fractions of integral domains. So, let R be an integral domain. Okay. So, what is an example of an integral domain? So, let such an example Z is such an example, and let us look at the relation between Z and Q. So, Q is a field containing Z, right? Q is a Q field containing Z. Every element of Q, it looks like this, P by Q, where P and Q are integers, Q non-zero. So, basically Q is the field, obtained by considering all fractions of elements of Z, right. And then one more thing we should also observe, that suppose F is a field such that there exists Z2 as a 1-1 homomorphism. So, suppose F is a field such that from Z to F there is a, suppose phi is a injective homomorphism. Suppose field, let me put it in this way, and then it is very obvious to see that the following, if I put it, let me rather accomplish that by drawing a diagram. Suppose this is my F, and this is the standard inclusion that every integer is being now viewed as the rational number, A is being viewed as A by 1, and this is where I have F. Okay. So, I define phi bar in such a way that phi bar of A by B is phi A by phi B. Okay. It can be shown that in fact that routine verification I am leaving to you, that it can be shown that the phi bar defined in this way is actually well defined. Okay. So, what we have seen is whenever there is a one-one homomorphism from Z to any field, then that extends to a homomorphism from Q to F. Okay. That is what you can immediately see. So, this is what we have observed for the very known integral domain Z. Now, what we are going to do is we are going to generalize this phenomenon for any integral domain. Okay. So, what we are going to do is the following: given any integral domain R, we are going to show that there is a field called let us say Q, such that whenever, so let me write it as better. So, I will explain the heuristics as well. So, given integral domain R, maybe I should directly write down the statement. So, this is called universal property of field of fractions. So, what it says is, given any integral domain R, there exists a field Q and a 1-1 homomorphism from we denote this by I from R to Q, 1-1 homomorphism, such that the pair Q comma I satisfies the following property. Satisfies the following property. So, what is the property which we are talking about? So, first let me write down the statement, then I will explain what is the property. Satisfies that whenever F is any field and phi is a R to F, and whenever we are given a field F and a 1-1 homomorphism from R to F, then there exists unique homomorphism phi bar from Q to F such that the following diagram commutes: R to F phi, okay, that is phi bar phi. Okay. So, this is what we are going to prove. So, before I get into the proof, let me try to explain what it means. And okay, so another way, let's for our simplicity, let's call this as the property star. This whole thing, let's call it the property star. Okay, and furthermore, if let us say R1 I1 and R2 I2, sorry, Q1 I1 and Q2 I2 satisfies property star. So, what I mean by this here is, here Q1 is a field, this is a field, and I1 is a 1-1 homomorphism from R to Q1. Similarly, for I2, so if we have two pairs Q1 I1 and Q2 I2, both satisfies this property star, and of course Q is replaced to be Q1 and Q2 accordingly, then there is a then I say, let me simply put it that then Q1 must be isomorphic to Q2. So, this is the whole statement that we are going to prove first. So, before getting into, so the statement is written in a very technical language. Let me first explain and extract the intuitive meaning for that. So we are given an integral domain R. We want to talk about a field Q. Okay, we want to talk about a field Q. What's the relation between this R and Q? From R to Q, we have a natural impedance, a 1-1 and 2. That's a 1-1 ring homomorphism. So, thus this R now can be regarded as a subring of Q. So, therefore, our situation is the following, that we are given some R, we want to say that there is a Q, we are given an integral domain R, we want to say that there is a field containing R. So, here containment is, here R is, since nothing else is specified, so R is regarded R is considered to be say identified with its copy inside Q. So, given R, there is a field Q such that what happens is whenever we have a 1 on map from R to F, that is again by whenever we have a map from R to F, then that map can be extended all over the Q. Okay. So, you see this is exactly the phenomenon that we have seen earlier for Z and Q. If you have a map from Z to any field or 1 on 1 homomorphism, then that extends to a homomorphism over whole of Q. So, this is exactly the phenomenon we are going to establish, we are going to prove here, that whenever we have a map from R to some field, that means there must be a map from, that map has to be extended from all over the key, all over the field Q. And the next part says that, so in the first part given R, there is a pair Q comma I satisfying this property star. The second part says that if we are given two such pairs, both are satisfying the property star, then the fields will be isomorphic. So, what does it say? It says that given R, the field Q that satisfies this property, that field must be unique up to isomorphism. Okay. To be somewhat more loose, so whenever we have a 1 homomorphism, if we want to then regard R as a subring of F, so then everything can be loosely translated. Again I am saying it is loosely put in the following manner, that given R, there is a field Q containing R such that if any other field F contains R, then that must contain Q. Okay. If any other field that contains R, then that must contain Q. So, this is what it says that. So, thus it is now legitimate to say that Q is the smallest field, smallest in the sense of containment, smallest field containing the given integral domain R. Okay. Because Q contains R, if a field contains F, again this time I am getting quite sloppy, if a field contains R, then it must contain Q. That is how you have to perceive this property. Okay. And technically speaking, every 1 homomorphism defined from R to F, R to any field, can now be extended to a homomorphism to over whole of Q. Alright. So, I have to prove this. So, first we have to show that, in fact like the proof is very routine. I will just tell you the main steps, the rest you have to figure out, and we will just basically mimic the construction of Q from Z. Okay. So, how to do that? So, we consider the following pairs A comma B, where A belongs to R and B belongs to R minus 0. Okay. We consider this. On X, let us define a relation. A comma B is said to be equivalent to C comma D if and only if AD equal to BC. You will realize soon that why the relation is this, why we are going to consider this relation. So, in view of this relation, you can easily check this is equivalence. Check. Then we consider X mod tilde. So, X mod tilde thus. Okay. So, given any equivalence class here A, B, from now on we will denote this by A by B. Okay. So, and you can immediately check that if A by B equal to C by D, I mean the notation is defined in a well coherent manner, if I C by D, then actually the AB is related to CD, okay, that you can immediately check. So, now we are going to consider this collection on which, so this is what we let Q be this set, and on Q we are going to define an addition and multiplication. So, I will define that. This is defined in very natural manner, the way you define, the way you multiply rational numbers. So, it is safe to take two elements like this from Q, we define this by AD plus BC by BD. Similarly, A by B to C by D, we simply define the AC by BD. Remember that all these are equivalence classes. Okay. So, I leave you to check that these are well defined. These are well defined, and then it is quite the next step is you can immediately show the way these are defined. 0 by 1 is going to be the 0th element, 1 by 0 is going to be the multiplicative identity, and that is how this operations is going to make Q a field. Okay. So, this is the field Q. Next, what we are going to do is, all right, I think I can erase this part. We are going to erase this part. So, we have obtained a field Q, and next thing is we have to show an inclusion I. So, we defined R from R to Q as follows: I of A is defined by A by 1 for every A in R. The verification that this is 1 1 is again quite obvious. So, I leave the checking to you. So, these are just manipulations. Now, so therefore, now we have obtained Q and I. Now, I have to show that Q, this pair Q and I, that is this Q and this I, they satisfy the property star. In order to show it satisfies the property star, what do I have to do? I have to start with a field F and the homomorphism. Okay. So, suppose I am given a homomorphism phi 1 1 onto 1 1 homomorphism, then from Q I am defining the following map, let us phi bar. So, how is that map defined? R of a typical element of Q is like defined like this, and then like here you see that we do not have much choice. Okay. This will be very automatic, because if this is an homomorphism, this is what you must have. So, okay, maybe right here I should write that directly, then you can check phi A by phi B. Of course, you check that it is well defined. So, again the way it is defined, just a manipulation shows that this is a homomorphism from Q to F, and more importantly it commutes this diagram, because here you see that a typical A is now being moved to phi A. Now, here it is come A by 1, and where it is going is phi of A by 1 is phi A by phi 1, and since it is homomorphism, phi 1 is 1. So, for this we have checked that this phi bar indeed satisfies this commutative diagram, and also we have to show that given phi, this phi bar has to be unique, because that is what it is said that given phi there is a unique phi bar from a Q to F. What we have just proved is we have constructed Q and I such that for any given phi we have shown that there is a phi bar that makes this diagram commutative. We have not shown that such a phi bar is unique. So, that is again quite obvious, which in fact I was doing a few minutes back, that if phi bar satisfies this commutative diagram, then okay. So, let me use a different notation. Let psi satisfies this commutative diagram. let psi satisfies the commutative diagram, then what must have is psi of A by B, it should be, so A by B can be written as A by 1 times 1 by B. So, psi of A by 1 and then psi of 1 by B. So, now you see psi extends, I mean psi satisfies this commutative diagram. So, that means this has to be phi of A, and psi of 1 by B, this has to be the inverse of psi of B by 1, right, because psi is a ring homomorphism, and therefore, it is nothing but 1 by psi of B by 1, which is again phi of B. So, it shows that if psi is a homomorphism that satisfies this commutative diagram, then psi must coincide with the fiber that we have defined. So, this shows that given any phi, this is we have a unique fiber homomorphism, namely the one defined by this, which satisfies the property star. Okay. So, let me again summarize what I have done. Given any x, given what we have done is the following, that given R, we have constructed a field Q. Of course, I left the verifications for field to you. There is we have constructed a field Q and a inclusion homomorphism, that is a 1 1 homomorphism, this such that the pair phi comma I satisfies this whole property star. What is the property? Whenever you will give me a phi, I will produce a unique phi bar. I will show that there is a unique phi bar that makes this diagram commutative. Okay. This is what we have done. Heuristically speaking, if we have a map in 1 1 map from R to F, then that map extends to whole of F, and that extension is also unique. Okay. So, that given any map from R to F 1 1 homomorphism, that uniquely extends to whole of this Q. Okay. So, that has proved the property this up to this. Now, we are supposed to establish the uniqueness of this, and here the proof of the uniqueness part is again very routine, not, in fact, this is quite entirely independent of the proof of existence. So, this kind of functorial arguments you have seen earlier. In fact, later on you are going to encounter again and again. This is an excellent kind of, this is a very, very common functorial argument. So, what is given to us? Given us that a pair Q1 I1 that satisfies property star. Okay. We have given two pairs Q1 I1 and Q2 I2 that satisfies that star. Okay. So, we take Q1 I1, since this satisfies the property star. What does that mean? Whenever a field will be given and the injective homomorphism will be given, then there will be a injective homomorphism, of course, because it is between field to field. Whenever injective homomorphism will be given, okay, let me again repeat. So, whenever a field will be given and the injective homomorphism from R to that field, then that there will be a homomorphism from Q1 to that field, which makes this diagram commutative. Okay. So, now you see that according to our assumption, Q1 is a field and this is an injective homomorphism. So, since this satisfies property star, that means there exists a phi homomorphism that makes the following diagram commutative. Let me put it in this way. So, R2, so try to understand here, we assume here we first take Q1 comma I1 that satisfies property star. Now, we are using that it satisfies property star by considering F equal to Q2 and phi equal to I2. Okay. So, therefore, there is a homomorphism, let us say phi that makes this diagram commutative, right. Now, we reverse the role of Q1 and Q2. So, now we focus on the fact that Q2 comma I2 satisfies property star. That means, whenever a field will be given, we will and a homomorphism, field and a homomorphism will be given, we have something. So, here as the field we take the q1. So, that shows we have another homomorphism, let us say psi, such that this commutes. I have deliberately put them together, right. So, this kind of argument you have already seen. Now, what you do is you simply take the psi compose phi, which is a map directly from q1 to q2, and do this diagram separately. I2, here we have phi compose psi. Okay, good. Now, you see that now we use the given any phi, the uniqueness of phi bar. You see that given given this field, given q2 comma I2, if we take the same field and the same homomorphism, already we can see the identity map is the identity homomorphism commutes this diagram, right. The identity. So, again let me explain. So, here we are using the fact that this satisfy property star. So, that means whenever a field will be and a homomorphism will be given, then there will be a phi bar. So, here in this situation I am taking I am taking q2 as f and phi as, okay, and this homomorphism as I2. So, this by property star there will be, I know that there is a unique map, that unique homomorphism that makes this diagram commutative, right, and in fact where you can check the identity commutes the diagram. So, therefore, identity turns out the unique map that makes this diagram commutative, and here also, and now come back here we see this makes the diagram commutative, therefore, we obtain phi compose psi's identity, phi compose psi's identity. In the similar fashion, we can show psi compose phi's identity, that shows both phi and psi are isomorphisms. So, this is an excellent like this kind of functorial arguments you have encountered earlier. So, how is it done? So, first you take q1 comma I1 and use the fact that it satisfies property star. So, here as f you take q2 and as this homomorphism take R2, take phi 2, take I2, then therefore, you obtain a homomorphism, you obtain this homomorphism, you do the same by changing the role of q1 and q2, then you get this. Now, if you take their composition, you see that this is the diagram what you are obtaining. Now, on a separate note, since q2 comma I2 satisfies property star, so in the property star if we take f equal to q2 and phi to be that and this phi to be that I2, then we see that identity is the one and only one homomorphism that makes this diagram commutative, and earlier we have seen this makes this diagram commutative. So, this has to be equal to identity, similarly the other composition. Okay. So, this proves that if for a given R, if we are given two such pairs, then they are going to be isomorphic. So, up to isomorphism for any given R, there is a unique Q. Okay. So, in fact, we have constructed the Q. So, try to understand the point. While proving the existence, we have constructed Q in some way. Someone might end up with some different construction, but the thing is they will be isomorphic. So, therefore, of isomorphism we can safely now regard that the Q is nothing but the field consisting of all fractions of elements of R. So, this R, so given R, this Q is now being called as the field of fractions of R, right. So, that you see that this is nothing but a generalization of the relation between Q and relation between Z and Q. So, therefore, what are the examples? One immediate example is what like we have started with, that is namely Z and Q. Another example of field of fraction is, so I will quickly tell you and then I will simply move to Hilbert's Nullstellensatz. So, what are another example? So, here we take f to be this integral domain where capital F is a field, okay. And so if this is my R, you can check that, oh sorry, the field of fractions. So what is this? The collection of all rational rational functions f and g, both g not equal to 0. So this field of rational functions, so this is going to be, you can check that this satisfies this property. So therefore this, the field of rational functions becomes the field of fractions of ring of polynomials, okay. So you see that here also the phenomenon is exactly similar to that of Z and Q, okay. So there are other examples of fields of this field of fractions, but right now let me permit me to get back to our original discussion. So as I said that I will be proving Hilbert's Nullstellensatz. It's a very important, it's a celebrated result that establishes a very important connection between algebra and geometry. So I will explain why, I will explain what I exactly mean by this. Hilbert's Nullstellensatz so as I said, it is the generalization of the phenomenon that you have seen earlier. So so we start with a polynomial ring in n variables, okay, over C, and let A1 to n be in Cn, okay. So now consider the substitution homomorphism. Consider the substitution homomorphism, which is a homomorphism from C1 up to Xn to C, which satisfies, okay. Earlier we have proved that such an homomorphism exists. So given C and a point, given this and a point this, we consider the substitution homomorphism. Now the point is that let also denote MA by kernel of SA, then first of all MA is maximal. Let me write down the conclusions one by one over there. Then for first of is MA is maximal. The second conclusion is MA is generated by these polynomials. So this is generated by let me write this, is generated by these polynomials x minus x1 minus up to xn minus this. So that is in notations, this is okay. And the third one is very important. Every maximal ideal is of this form. Maximal ideal of the above form. So, therefore, what does we will prove this theorem, but let me first explain what this theorem says. This shows that, like that we have seen for single variable polynomial ring, that the maximal ideals of the polynomial ring in n variables, that the maximal ideals are in bijective correspondence with the points of Cn. Okay. So, corresponding to every maximal every point we do have a maximal ideal, and any maximal ideal is given uniquely by such a point. Okay. So, one thing is, I think you are convinced that if we have two different points, then the corresponding ideals generated by them are going to be different. That is quite clear. Okay. So, that part I am leaving assuming that you know, assuming that you can see immediately, that is if A1 to An and B1 to Bn, these are two different tuples, then the ideals formed by them in this manner are going to be different. Okay. So, as I said, Hilbert's Nullstellensatz, it establishes a connection, an important connection between the ideals of this polynomial ring and the points in that, and the points in Cn. And then we will use Hilbert's Nullstellensatz to we will use this this theorem to see more important connections. So, first let me give a proof of this. So, okay. So, what do I have to show? First, you have to show that this is this MA is maximal. So, what is MA? MA is this kernel of this. Now, you see that first of all, the kernel cannot be trivial, right? Because this is for example, the polynomial x1 minus y a1, this is also by the evaluation map, this is also going to 0, and x2 minus y, that is also going to 0. So, therefore, of course, like one thing is very clear that, let me put it, write down the proof. Observation is xi minus ai, they are contained in kernel SA. Okay. Now, kernel SA, and of course, this map is onto, that is also quite clear. Okay. So, therefore, this ring modulo kernel SA is going to be field isomorphic to the field C, hence the kernel must be maximal. So, therefore, let me directly prove one here. It is clear that this ring kernel SA isomorphic to C, this exactly because of the constant polynomials are being evaluated to exactly at that constant. Okay. So, therefore, this is maximal. Okay. So, next we have to show that these are generated by this, these are generated by this. So, even that part is also not difficult. So, for the sake of simplicity, first let me assume x1 up to a1 up to an all are 0. I will do the general case, but we will show the general case follows from this case. So, therefore, we are now considering the substitution map S0. So, now observe that like if f(x) belongs to kernel of S0, what does that mean? It means that f of 0 0 0 is going to be 0. That means f has the constant term of f, the constant term of f is 0. Okay. So, if the constant term of a polynomial is 0, then every monomial, so then f is basically of this form, that some coefficient times x to the power I1 up to x to the power In, right, x1 to the power I1 up to xn to the power In. where since f has 0 constant term, so that means this has to be non-zero and all ij's cannot be 0, right, because f has no constant term. So that immediately shows that every monomial here is actually divisible by, every monomial is a multiple of some xi, right. Every monomial is a multiple of some xi. Therefore, from that you immediately conclude that f is generated by, f is contained in the ideals generated by x1 up to xn, right. And so therefore, kernel of S naught is contained inside the ideal generated by x1 up to xn, and x1 up to xn, they are already inside the kernel because the evaluation is at the point 0. So therefore, thus we get they are the same. So thus we have established the theorem in the very special case of a1 equal to a1 up to n is 0. Okay. Now let us do the general case. The general case is actually this is nothing but something called, as you can, many of you might have already realized this, you have to just change the variables. So what it exactly means is C1 from Cxn up to Cxn, we do have a homomorphism, ring homomorphism, which sends each xi to xi plus ai. Okay. So that is again substitution principle, because xi plus ai, these are in this ring. So you can do it, and once you, so let us call this map psi. So now then you can immediately see that here this SA, and if you take it psi, then these actually commute, right, because SA is the homomorphism that sends, so that sends each xi to ai. Okay. Now you see, so if you take the compositions of S naught and phi, that is also a homomorphism from this to that and sending again xi to phi, so they must be same by the substitution principle. So therefore, so another thing that you can immediately, of course, immediately see that this psi is a isomorphism, is an automorphism, because psi inverse is sending each xi to xi minus ai. So like you have a automorphism here. So under this automorphism, the kernel of this map goes to, since they are connected like this, goes to the kernel of that map, like the kernel of SA is being by psi is being mapped to kernel of S naught, and kernel of S naught is maximal. Therefore, since it is preserved on the maximality, all these are preserved on the isomorphism. So kernel of S is again going to be, so psi, observe is psi is isomorphism, and psi of kernel of SA is exactly kernel of S naught. That shows kernel of SA is a maximal ideal of, kernel of SA is a maximal ideal of the polynomial ring. Okay. So therefore, so loosely speaking, we are just shifting the, we are just giving a linear change in the variables, right. We are just giving linear change in the variables, and precisely what this means is we are factoring through this isomorphism. Okay. All right. So now let us try to prove the third part. The third part is actually harder to prove. The proof might be somewhat, it is actually long. So I will try to finish it today only. Let us see. So now we are going to prove that every maximal ideal is, so given any maximal ideal, there exists a point a1 up to, there is a point that is a tuple a1 up to n in Cn such that the given ideal, so proof of 3. So let M be a maximal ideal of this ring we want to show that there exists a point a1 up to n such that m, the script m becomes m of a. Okay. So, then what the way we will prove is the following. We first consider the ring of quotients, this quotient ring. So, since this is a maximal ideal, this is going to be a field, okay, and we do have the canonical projection map. So, this is just the projection map, right. We restrict this pi, restrict pi to Cx1. Okay. So, the same pi we are now restricting that to Cx1, that is now it is a map from, okay. So, let me denote this for the time being by phi, and one thing is very clear that in the image we do have the whole of C, right. So, so in the image we have the whole of C because each complex number z is now being moved to z, complex number z plus m, right. So, this image contains a copy of C. Now, the point is the following, that what happens to, let me put this question, what happens to kernel of, what happens to kernel of phi. So, earlier we have seen in the beginning of this course that what we have observed, that in this case the kernel is either trivial or it is going to be a maximal ideal, right. So, because this is an integral domain, so therefore, we have two possibilities, either this is 0, or it is a maximal ideal. So, that means it will be generated by some x1 minus a1 for some a1, right. Okay. So, suppose that we can show that this possibility does not occur, and not only that, I should have also been somewhat more precise, that I mean not only just restricting this to Cx1, if I restrict this to any Cxi, suppose I can show that I can, okay, let me put it in this way, suppose that I am able to show that after restricting this pi to all Cxi's, the kernel, after restricting all of them, I mean restricting this pi to all Cxi's, the kernels are not going to be trivial, then that means, okay, so I think the better way to put that is calling it phi I, yeah. So, suppose that I will establish the, suppose that for every I, the kernel phi I is not phi, okay. Suppose we are able to show this, then that will immediately implies that the kernel will be generated by some xi minus ai, right. And this is the kernel of the restriction. So, therefore, that is going to be, the kernel of the restriction is always contained in the original kernel. So, therefore, it shows that all xi minus ai's will be in the kernel of pi, right. Suppose we can do that, yes, so yeah, just a minute, maybe I should erase that. So, did I, okay, so, okay. So, therefore, then in the kernel, so suppose I can show that for no i's kernel phi I is trivial. So, therefore, then kernel phi I will be kernel phi I will contain all xi minus yi's, okay. So then that will imply, if this will imply all xi minus yi's, all xi minus ai's are inside the kernel of phi. What is kernel of phi? This is M. Now you are done, right, because M contains all these polynomials xi minus ai's. So what I mean is, this means MA, for this A1 up to n, MA, A is A1 up to n is a subset of M, but since MA is maximal, so therefore, I mean since both are maximal ideals, so then you must have equality. So try to again understand the line of the argument. It simply says that if we are able to show that for every I kernel phi I is non-trivial, then kernel phi I will be generated by something like this. So then we see that this must be inside M, and what is MA? MA is basically the ideal generated by this, that we have already seen. So therefore MA will contain M. Earlier we have proved MA is maximal, so that will force MA to be M. So now our job is to show that for any I, whatever I we choose, kernel phi I cannot be trivial. Okay, and showing that is not difficult. So now for the sake of simplicity, I am dropping the subscript from the notation and simply considering Cx, okay, and dropping subscript from the notation and simply define that by Cx. So okay, so all right, no, maybe for the time being, let's take x Cxi or Cn any Cx. So from there we have, so okay, so let this call as phi or phi I. For simplicity you can drop this. So now, so this is a so this is something. So if, okay, so what are we going to prove? We are going to arrive at a contradiction if kernel is empty. We are going to arrive as a contradiction. So that means this is an injective map, therefore it will extend to a unique homomorphism from the quotient field. So x1 you may write, or if you again, as I said, that you can simply drop from the notation. So there is a homomorphism, so this phi extends to a unique homomorphism from, of course it has to be injective, from this field to that field, okay. Now I am going to show that this indeed this is something not actually good. So how do I show that? So okay, so let me put it in this way, that we will do it by a series of observations. So the first observation is, so from C to this normal map that I just said a few minutes back. So this map is actually, so this is a this is a 1-1 map, because of course from a field to another field every homomorphism must be 1-1. So therefore the thing is, the observation is, this can be regarded, in fact let me make it in a somewhat more general, that suppose we are having a field and we are having an injective homomorphism from field to any ring R, then R has a F vector space structure. Okay, that's obvious. The addition will be just the addition of A, and the scalar multiplication will be, so alpha times R is defined at phi alpha times R. Okay. So whenever we are having a injective homomorphism, we see that then this can be, so yeah. So, in view of this, we can now regard this as a vector space over C. So, complex vector space, and this is countably generated because observation is there is a countable spanning set of this vector space. That is actually quite obvious. So, why do not you just take all the monomials of this form where I1 up to In are non-negative numbers. Okay. So, the set of all, so given any I1 up to In tuple of non-negative integers, we get a monomial. So, such tuples are countable in number. So, therefore, this is a vector space which is having a countable spanning set. Now, we are going to basically recall some standard exercise in linear algebra, which is again a very general one. Maybe I can just put it as an exercise, that first of all let V be a vector space over F. I do not know anything about F. F is just some field, not necessarily Q, R or C, just as a general statement. And suppose V1, V2 is a countable set spans the whole of V. So, now what you do is define Vn to be the span of, okay. So, easy to see that. In fact, I think I am not leaving it, as I am in fact doing it. So, you can just take this as a proposition. Easy to see that V is going to be the union of all Vn's, okay, because every vector you take, that will be a combination of these Vi's at some of beyond a certain stage, all the coefficients will be 0. So, then V is going to be contained in the corresponding Vn. Now, if L is a linearly independent set, then VL is same as L intersection V is same as L intersection Vn, right. So, L intersection Vn, so L is a linearly independent set. So, this is going to be a linearly independent subset of Vn. So, this is going to be a subset of L. So, thus this is a linearly independent subset, linearly independent set, and this is a linearly independent set contained inside Vn, right, and Vn is finite dimensional. So, this must be finite. Okay, this must be finite. So, thus what you have obtained is L must be countable. So, the upshot is, if a vector space is countably generated, then its every linearly independent subset is countable. There cannot be any uncountable set which is linearly independent. With this, we now finish the proof of the Nullstellensatz. So, here this is going to be our V. So, this is a complex vector space generated by this countable set. So, in order to arrive at a contradiction, we must exhibit a uncountable set which is linearly independent. So, my claim is, what about this collection 1 by let us say xi minus ai, okay, ai may not be, just a minute, a has come, so what about this, that Okay, so let me for simplicity, okay. So what about this collection? Let's say z minus, well, not exactly this. Let me first try with this. What about alpha in C? What about this collection? Not I think I should simply write down alpha belonging to C. Does this work? Does this work? So this is of course an uncountable set, uncountable subset of this polynomial ring. So I just have to show that this is a linearly independent subset. So that means, so linearly independent. So if it is linearly, if it is okay. So yeah, if it is linearly dependent, that means one must have points. One must have points such that alpha, not necessarily some other scalar, equal to 0, right? And not all bi is 0. Not all bi equal to 0. Okay. So one must have this, but actually then now it is easy to see that this is indeed a problem, because we can view this as a function from C to of course C to of course C. What is the function? We view this as a function from like this, beta I by z minus alpha I, z minus alpha I from 1 up to n. So this is a function not defined everywhere, z minus C minus the points, okay, C minus these points. So if this is 0, then this function must be a 0 function, right? If this is 0, then this function must be a 0 function, because then whatsoever values of x1 other than alpha n up to alpha n, it should give you the value 0, but that is not actually the case, because let us say not all bi 0, so there is some bj which is non-zero, right? So I mean it is easy to see in this term z minus alpha j, if you take z minus alpha z is very, I mean I am just like giving you the main idea of that argument. So it is actually obvious, you can complete the rest. So for this term bi, if you take z close to alpha z minus alpha j, so in the denominator is getting closer and closer to 0. So therefore this term will have very very high modulus, very high absolute value, and that prevents this function being 0, I mean everywhere in its domain. Okay, let me again explain. If I take z to be like this is analytic argument using epsilon delta. So the idea is if z is closer to alpha j, then since this is getting closer to 0, so the absolute value for that will be very very large. And of course in that situation other terms will not disturb at all, because like alpha is a distinct, so for other terms there will not be any problem. So the I mean the upshot is then this function takes, I mean very very high values, okay, near this function takes very high values near alpha j. So therefore this function cannot be a 0 function. So therefore thus we arrive at a contradiction. This shows that whatever I you take, the kernel cannot be, whatever I you take, the kernel cannot be trivial, because if the kernel is trivial, then like as I have already shown that you have a like yeah. So in fact that is exactly, I have shown that if kernel phi I is trivial, then you do have an injective homomorphism from Cxi to field, and in view of this, then this is what you obtain. Okay, so there is a few just little gaps in the argument, which I think I should give a few clarifications for that, just to make sure that earlier what we have observed that earlier just what we have observed, I will just quickly give the clarification. So, if let us say phi 1, see this if let us take phi 1, if kernel phi 1 is 0, so the argument what we are giving is that essentially goes for every phi I. So, then this extends to a map from the right. So, therefore, this contains a subfield isomorphic to Cx1. So, Cx1 is basically just one variable ring of one variable field of fractions, and okay. So, and then C, and then from C to Cx we have the very natural inclusion. Every constant function is now being as the constant rational fraction, and from here we have this phi 1 tilde. Okay. And therefore, we do have a homomorphism from C to here. It is an injective homomorphism. So, the point is that here this it is not actually correct to say that this map Z is being equal to Z plus M is a injective homomorphism. That is not yet clear, because okay. But however, the thing is maybe this one I can avoid, because I need argument, different kind of argument over there. That's better. So, this is the situation, and therefore, Cx is, so this is a vector space. So, this vector space, every linearly independent subset of this vector space must be countable, but now we see that a subspace of this vector space here, this is admitting a uncountable linearly independent subset. Therefore, that is how you arrive at the contradiction. Maybe that is a much clear cut argument. Okay. So, the thing is the following, that like C is naturally embedded inside Cx1, Cx1 is by means of phi 1 naturally has an embedding inside this. So, thus with respect to this composition, we make this quotient a vector space over C, and this is of course countably generated. Then this is also countably generated, because any map here is just like this and generated by this, and therefore, being a subset, this has to be, this cannot contain any uncountable linearly independent subset, but it does contain. This is the contradiction. Okay. So, with that finally I finished the lecture.